Hello, and in this video we're going to look at converting binary into hexadecimal and then hexadecimal back into binary. So we're first going to do a quick recap on how we produce the colour of a single screen pixel, and we're going to start by looking at white. So to produce the colour white on a screen pixel, as you can see in this background here where we've got white, to get that colour you are actually seeing three different colours all set to their highest value. There are three filters: red, green and blue, also known as RGB, and each of these, when they're up to their maximum and overlaid together, create the colour white. And all of these have to be on to a maximum. Now in hexadecimal, which we've not fully looked at yet, but hexadecimal, this is represented with the highest value, and that is FF, FF, FF. Each channel is up to its highest value and we get white. Now the denary representation, the highest denary value of 8-bit is 255. So each of these colours would be up to their highest value if it was denary as 255. And in binary, this is represented by the binary 8-bit highest value, the highest byte, which is 11111111. And so all of these are up to their highest value, and that's how we get the colour white when they're overlaid. Now, to use binary would require the use of up to 24 digits, and you know, when you're creating lots of colours in different pieces of artwork, that's a lot for an digital artist to have to remember and use. It wouldn't be practical for us to remember each of these for creating some artwork that would be displayed on the screen. It would actually be a lot. Now here, what I've done is you can see the binary values, and I've got the colour in the background is the colour that they are. So we've got this kind of really dark red, this green, which is up to its maximum, and then we have this blue. And we can see the 8-bit pieces of binary that they are, that get them there. So the denary values of these are 29, 255 and 147. So this is quite low, and this is in the mid-range, and this is the highest. And you know, even to use denary, this still requires the use of 9 digits, and although that's a significant reduction, more than half of the 24 required to use binary, it still could be more efficient, and we can do that by converting again to hexadecimal, as this would require the use of only 6 digits. So we've got 1D FF93, and at the moment that seems really random, but as we'll see when we do the conversions, actually it does make a lot of sense. So finally they create the red, blue, green, and as we've said before, when we overlay those three filters together in a single pixel, we then get the colour. So all of these, this red, this green and this blue, make this colour appear on screen, which is pretty cool. So let's have a look now at how we actually get from binary to hexadecimal and from hexadecimal back to binary. Okay, so now we're going to look at converting binary to hexadecimal. So we've done some of this in class, however we're going to re-practice it again today. I'm going to run through it, practice it on the worksheet so that we're confident in working with this. So we're going to start with the value, the 8-bit binary, the byte 11101101. And the first thing we need to do is split that in half. So we've got 1110, and then on the other side we've got 1101. We're then going to map out 4-bit space values 1, 2, 4 and 8, but in reverse, as we did before when we converted binary to decimal. As before, we're going to place 1s and 0s, the binary code underneath, and we're going to keep the 1s and disregard the 0s. We will then add them up, which in this case will create a value of 14, and this step says that any that are between 0 and 9 stay the same, any that are 10 to 15 need to be converted to a letter between A and F. So let's look at that table. Now normally this table would run from 0, 0, 1 equals 1, 2 equals 2, 3 equals 3 equals 3, all the way down to 9 equals 9, and then it will go 10 is equal to A, 11 equal to B, 12 equal to C, 13 equal to D, 14 equal to E, and 15 equals to F. And the reason for that is that we get additional single digits. To use 10 would confuse the system, so by using a letter it creates a single varied digit. So 14 is actually E, so we carry the E forward, and let's look at the other side now. So we place those values in reverse, we place our binary underneath, we keep only the ones, we add them together, and then if it's a double digit number, so anything above 9, it will need to be converted, and 13 gets converted to D, and that leaves us with a hexadecimal of ED when we put them next to each other. So the binary 11101101 has a hexadecimal value of ED. So what I'd like you to do now is to use this same process to answer the questions on section 1 of the worksheet, and pause the video. So take a moment to pause the video, complete section 1 on the worksheet, and then come back. Okay, so welcome back, and this time we're now going to convert hexadecimal to binary. So we're going to start with the hex code value E3, and we're going to convert that back into binary. So we're going to start by splitting the two digits E and 3. I'm going to start with E, and I'm going to come back to 3 later. So E, as we know, is a letter, and in this case we have to convert it back to a number. So E equals to 14, and so we're going to start with that value, and what we need to do is place out 4 value channels, starting with 1, doubling each time, so 1, 2, 4 and 8. And then what we're going to do is basically put our value in, 14, and if we can take this value out of it, we will. If we can't, we carry it over. So let me show you what I mean. So we're going to place 14 above 8. Can we remove 8 from 14? Yes, we can. So that gives us a value of 1. And then we're going to carry the rest of that sum forward. So 14 minus 8 leaves us with 6. We carry the 6 forward, but because we were able to take 8 out of 14, we put a 1 here. So we now have 6. Can we remove 4 from 6? Yes, we can. So that leaves us, we place a 1, that leaves us with 2. So 6 minus 4 equals 2, which we'll place up here. But because we were able to do that sum, we put a 1. So we now have 2. Can we take away 2 from 2? Yes, we can. So we place a 1, and here we're going to have 0. Now we have 0. Can we take 1 from 0? No, we can't. So therefore we place a 0 underneath. Okay. When we look at the next one, number 3, we'll see this happen again, and it should hopefully be really clear what to do fully then. So keep with the video. So write out the binary digits in order, and that leaves us with 1110, which actually, if we go back in the video, we'll see that we got E from that very same value, so we know it's correct. So let's have a look at the other side of this now, this other hex code 3. So because it's 3, we don't need to convert it. It doesn't matter. It's not a letter. We don't need to use this table. If we look at a full table, it will say 3 equals 3. We don't need to do that. So we take 3, and we're going to start again by placing our value channels out, 1, 2, 4 and 8, and we're going to start with 3. So we're going to ask the same question. Can we take 8 from 3? We don't want any minus numbers. So no, we cannot. So because we can't do that, we put a 0. And we carry the 3 on. Now can we take 4 from 3? Remember, we don't want any minus numbers. So the answer is no. So we place a 0. And we're going to carry forward the 3 again. Now, can we take 2 from 3? Yes, we can. That's going to leave us with 1. So, because we can do the sum, we place a 1 and we carry the 1 forward. Can we take 1 from 1? Yes, we can. So, we place a 1 underneath. Okay, and that leaves us with 0, so we stop. We can't go any further. Now, if we were converting this the other way around, we know 1 and 2 makes 3. We've got 3 here. It all makes sense. It all aligns up. So we're going to carry that forward, and we have 0, 0, 1, 1. The final stage as before is to then bring those nibbles, those 4 bits together to create a byte, which is 8 bits, and we now have the binary value of the hexadecimal E3. So what I'd like you to do now is go to the worksheet, answer these questions on section 2. Remember, you must complete and hand the worksheet to me in class or your other teacher, depending on how your school will do this. And if you're at my school and my lesson, there will be a link on Satchel to a Microsoft form where you will need to put your final answers in, and to complete the home learning you will need to do both elements. But speak to your teacher to see if that is a requirement for you. Okay, if you have any questions for me, contact me on Satchel. Please do not leave any comments in the YouTube channel or messages. They will be completely ignored, and I will not respond. So please, only if you are a student, contact via Satchel. Thank you and good luck.